Hello and welcome to Checkpoint 4 for Group 12 for Stat 512. Our group is Suyan Chang, Caleb Day, myself, Avery Fry, Brittany Gear, and Philip Goldberg. So first for this checkpoint, we want to go through what we've done to improve our model. We'll go through step by step. First, we removed the outliers, just to remove those points that were really influencing our model. We looked at Cook's D, leverage, and studentized residuals, and just went ahead and removed any point any three of those identified as beyond the threshold. We performed ridge regression on this new model just to see what its suggestions were to do with our points, and then we applied those suggestions we found from Ridge back to our initial MLR model. So first, what we did was we removed our outliers. That was 32 different observations that we removed. This didn't really affect our estimates just crazy much, but it made us a little more confident in the ones that have a small p-value, and it also greatly reduced our residual standard error and our adjusted R squared. Next, we performed ridge regression, so we normalized our variables and we looked at what the coefficients were on these to show their impact, and we saw that percent population under poverty had a crazy high impact, and then percent not high school graduate and percent unemployed had very similar impacts. So we determined that this suggestion being put out by ridge regression was that we should regress based off of our percent population under poverty plus that percent unemployed plus the percent not high school grad combined divided by two, just to kind of combine those two variables that were having very similar amounts of impact on our predicted class. And then that brought us to this final improved model where we just have two predictors, our percent population under poverty and the combination of percent unemployed and percent not high school graduates. As you can see, this made all three of our values significant. It increased our adjusted R squared and reduced our residual standard error. In all, this just seems to be a better model due to, like I said, all of our betas being significant. So this is the improved model we're going to be talking about throughout the rest of this presentation. A little bit more on the results front of the differences between these models. Our final model had better AIC, BIC, and adjusted R squared compared to both our initial model and that model, which with the outliers removed. You can see that the biggest jump was when we removed those outliers. That makes sense because we removed some points that were creating a lot of noise in our data. So we're going to fit the data better, but we can still see that cutting down from 4 predictors down to 2 significantly improved our model as well across AIC, BIC, and adjusted R squared.
So in this analysis, we began by cleaning the data set and removing outliers, then standardizing all variables to ensure comparability across the predictors. And because the original model showed strong multicollinearity among poverty rate, unemployment rate, and high school dropout, we simplified the structure. We kept the poverty variable and created a new combined predictor equal to the average of unemployment and high school degree rate. So this left us with 3 coefficients to estimate, B0, B1, and B2. And to evaluate their stability and uncertainty, we bootstrapped the model 1,000 times by resampling the clean data set with replacement and refitting the regression each time. From these bootstrap replications, we obtained coefficient estimates, standard errors, and the 95% confidence intervals. And so for B0, the intercept, we observed very low sampling variability around 126 and minimal bias. Its 95% confidence interval does not include 0, indicating that it's statistically significant. And given the standardized predictors, the model suggests a baseline crime rate of 7,768 at the predictor average. For B1, the poverty coefficient variability was also pretty low, around 177, and the 95% confidence interval was entirely positive, providing strong evidence that higher poverty rates are associated with higher crime. And for B2, the combined unemployment and education predictor, the bootstrap variability was moderate around 191, but still reasonably stable. And its confidence interval was fully negative, indicating a significant disproportionate inverse relationship. The combined index is associated with a reduction in crime of roughly 680 units. And so overall, the bootstrap results confirm that each coefficient is statistically meaningful, and they give us high confidence in the direction and strength of these relationships.
On to a comparison with the original model. The first step is to compare the model with and without the removed outliers based on leverage and Cook's distance data. With all outliers removed, the estimates and most standard errors remain fairly consistent. The intercept standard error, however, does have a solid increase from 1360 to 1613. But this is an unrealistic expectation to actually happen in the model for all the predictor values to ever be zero. There is commonly going to be a percentage unemployed or not high school grad or a percentage under poverty. The police on patrol does have an interesting phenomenon where it switches from a positive to negative relationship when we don't have the outliers, which makes more sense. Having more police should realistically result in a lower number of crimes, but the model still does suggest a non-significant impact based on this data. Every other value holds their positive or negative relationships, but becomes slightly stronger. For example, the percent unemployed goes from negative 126 to negative 135. And in general, there is a stronger relationship for each variable. The residual standard error does greatly decrease when removing the outliers, and the R-squared increases, implying that more of the error is predicted by the model, as it increases from 0.412 to 0.4734. Moving on to the comparison between the model post-ridge regression in comparison to the removed outliers, the R-squared value and the standard error remain fairly consistent to the removed outlier case. The intercept error is actually vastly lessened in this case. It goes from 1613 all the way down to 130. This is interesting because a zero case is still unrealistic. You would still expect there to still be a percentage under poverty, and even with the combined unemployed and not high school grad percentages, that would still realistically not have a zero case. Poverty also shows a large increase in the effect, moving from a estimate from about 350 to all the way to over 2,000. The combination between the two negative relationships also shows a significant increase in their estimate, as well as the relationship with the intercept increasing.
I'm Brittany. I'm going to be talking about the model interpretation specifically for our coefficients. So this is our final model output from R. I went ahead and put this into a table so it's a bit easier to see. So our final model here, I have at the top, we have the crimes per pop equals beta 0 plus beta 1 times the percent population under poverty plus beta 2 times the average of the percent unemployed and the percent not high school grad. So these coefficient interpretations are a little bit different from our original model. For the intercept, we have a value of 7,767.9, so this is our beta 0. And the interpretation of this is that the crimes per 100K population is expected to be 7,767.9 when both of the predictors, so the poverty rate and the average of the unemployment rate and the dropout rate, are at their mean value. And this mean value is going to be 0 after standardization. So for our second coefficient, we have the percent population under poverty, and this is going to be our beta 0. We have 2,306.5, and this means that for every one standard deviation, it turns into one standard deviation instead of 1% after the standardization. So for every one standard deviation, the increase in the for every one standard deviation increase in the poverty rate, the crimes per 100K population is expected to increase by 2,306.5, while the average of the unemployment rate and the dropout rate are held constant. So then for our last coefficient, we have the average of the percent unemployed and the percent not high school grad. And this value for beta 2 is going to be negative 680.8. And this means that for every one standard deviation increase in the average of unemployment rate and dropout rate, the crimes per 100K population is expected to decrease by 680.8, while the poverty rate is held constant.
Okay, welcome. This is Caleb. Welcome to the final stage where we do assumption checking in this case. Now, of course, you have seen our, final model, but just for, in case you forget what it is, it's crimes per population equals to the percentage of population under poverty, and then the percentage of unemployment plus the percentage of not high school graduates divided by two. So this is our final model. We're going to check assumptions in this stage. So that is linearity, like whether or not there's like linearity issues between our y variable and our x variable. Is we're gonna check whether or not there's like constant variance, which we wanted. We also want to check whether or not there's normality of errors and whether or not there's like any significant outliers or influential points in this case. So the first issue we're going to move on to is linearity. Now, as you can see on both of our graphs here, especially on the left two graphs and the right graph, you see that there is some, curvature shown in both graphs between like both variables, well, both x variables and y variables, and then on like an overall and individual like level. So you can see on like the left two graphs. That's a partial regression. You can see there's some curvature on the overall model. You can see that there is still some sort of curvature there. And then moving on, we could then see, okay, we're not just constant variance. In this case, you can see like there is like some like you can see in this case variance isn't constant. So especially on the graph to the right, you can see that the spread of the variables, so not the variables, the observations or residuals aren't really constant in the graph to the right. And then looking at the we're looking at the Bruce-Pagan test, you can see that the p-value is less than 0.05, which suggests that, hey, the variance of our final model in this case isn't exactly constant, which is something we don't exactly want. Move on to normality of errors. You can see the distribution of the residuals is still, compared to the original model, is still skewed to the right. And then the Shapiro-Wilks normality test kind of like shows this with like, p-value equals 0.002533 in this case. And then moving on to the outliers and influential points, we can see that there's, 43, 207, 52, 15, and 19. Shoot, dang it. 43, 207, 52, 15, and 19. Those are like outliers. We have 1, 2, 3, 4, 5 outliers in this case. And to do like summary of this all, well, and then to compare it to the original model, which is this is our original model. So in this case, we can see that okay, our non-constant variance with p-value, So comparing this original model to our final model, we can see that the p-value for the original model is a lot lower for both the non-constant variance and the normality of errors for the original model. So, and then also the number of outliers for the original model is a lot lower in this case. For linearity in this case, you see that looking at the next slide, the original is on our left, the final model is on our right. You see that the final and original model looks about roughly the same in this case, are roughly the same. So overall, we can say that the final model, it still has the errors of residuals, and the heteroscedasticity issue. So in this case, we had like, and there's still also, so in this case overall, we have issues with errors, having not following a normal distribution. We have the issues of non-constant variance. We still have linearity issues, and we still have some outliers. However, in comparison to the original like model, it's still like in the original model, in comparison to the original model, the final model is an improvement in terms of errors, the number of errors, non-constant variance, and then linearity and all that, but it still needs improvement in saying, hey, we need like normality of error. We need like errors to follow normal distribution. We need non-constant variance. We also need to address the linearity issues, which are still present. So overall, the final model still, has issues that needs to be addressed, but compared to the original model, it's an improvement, though a slight improvement overall.